Good morning, everyone. Can you hear me at the back? Okay, great. So as you can see, the talk is on smart healthcare, and what we'll do in this talk is look at this healthcare concept from various directions. So to situate healthcare, it's really an IoT problem, and as all of you know, the number of things connected to the internet is growing year by year. By 2020, the expectation is that this number will reach 50 billion, and some say by 2030 it may reach 1 trillion. So that's a lot of devices, a lot of things getting connected, as opposed to just 4 billion humans who will be connected to the internet by then. And the net effect of this is just making things, different applications, smart. So homes and buildings and grids and transportation and medical devices, surveillance, everything is becoming smart. So in this talk, we'll just talk about smart healthcare, but the techniques that we talk about, a lot of them are actually more broadly applicable. So what is IoT? It's basically a collection of sensors, actuators, processing elements. You collect data, you distill intelligence from the data, you take some decisions based on that data. And according to McKinsey, the impact on the world economy by 2025, this is per year impact, is going to be between $3 to $6 trillion. And right now, the world economy is about 80 trillion. By 2025, it's going to be about 100 trillion. So that's 3 to 6% of the world economy coming from IoT. And biggest fraction of that, 1 to 2.5 trillion, is going to be from smart healthcare. Another way of looking at it is that out of the 100 trillion, about 25 trillion will go to healthcare, and 60% of that will go to chronic conditions. And these wearable medical sensors and devices, these are expected to cut the costs by 10 to 20%, which again comes to between $1 and $3 trillion. So this is the Cisco model. It has 7 levels and 3 layers in IoT. At the bottommost level, you have these sensors and actuators, processing elements. They talk to each other. You do some signal processing in the edge nodes. Then you transmit data further up into the cloud, and ultimately you serve the user. So what is happening with the increase in the number of devices is that there's a huge bandwidth problem. I cannot send all the data to the cloud. There is a huge energy problem. Just sending all that data to the cloud requires a lot of battery energy. So the trend is to push intelligence downwards towards the edge nodes. And the extreme of the edge node is the sensor node. So we'll see if it is possible to push intelligence, to push inference onto the sensor node itself. So here is the concept of the Internet of Medical Things, where there are lots of wearable medical sensors that are now becoming commercialized, and there are new startups being formed. And here in this figure, you see a lot of discrete sensors all over the body, and it's not that convenient. But what is happening is that these sensors are now getting concentrated into a sensor platform, and that's becoming much more easy to wear, something like a smartwatch, which will have lots of these wearable medical sensors. So going forward, it's going to be much more convenient to capture our physiological signals, and we have something in our pocket, the smartphone, that collects all these data and then sends it further to the clinic or the hospital, where the physician can look at that data, make sure that we are doing okay. So this is the outline of the talk. And as I said, that we'll look at smart healthcare from various directions. The first direction is disease diagnosis. So with these sensors now, is it possible to accurately do some disease diagnosis? And we'll see, we'll try to answer that in the affirmative with this system called Hierarchical Health Decision Support System. And we'll look at some application for stress detection and mitigation. Then I'd mentioned that there is a trend towards pushing the intelligence towards the extreme edge. So is it possible to energy efficiently do inference on the sensor? Because if you do more inference, the computation goes up, and we already are so battery constrained. So can we do anything more than sense and transmit with the IoT sensors? And aren't we going to drain the battery much more quickly if we do something more? So we'll try to see how to address that problem. Then if we are going to have these wearable medical sensors on us all the time, so now we can record our health for next few decades. So do we have the storage and do we have the energy required to be able to do that efficiently? And last but not the least, security is an angle for these medical devices that is often overlooked. And we'll look at some examples where if you don't bake security into the design, there could be a substantial problem later on that these devices could be attacked in terms of the integrity attack where you command the device to do something malicious. And so that has to be prevented. So a lot more work has to be done in security. Okay, so let's start with the first angle, which is on the health decision support system. It starts with wearable medical sensors. In 2015, 56 million were sold. This year, about 123 million are expected to be sold. And these are all kinds of sensors. ECG monitors your heart, your brain, your blood oxygen, blood pressure, and so on. And these sensors plus the smartphone, it's called the body area network, and plus the health server in the clinic, that's your personal healthcare system. There are all kinds of wearable medical sensors now. This is slightly outdated now. There are lots of startups. We just bought sensors from an MIT startup, which is very accurate. So accuracy is going up. They are being consolidated into a platform which is easy to wear. So accuracy is not an issue anymore with these sensors. And if you look at another thing that is enabling disease diagnosis with these kinds of sensors is in 2009, a HITECH Act was passed under the Obama administration, and $27 billion were made available for electronic health records. And that made clinical decision support more effective, and there is now evidence that, in fact, that has been true. It reduces preventable medical errors, which is, by some say that it's the third leading cause of death in this country. Assists physicians, gives diagnostic suggestions. So these clinical decision support systems, CDSS, have already had an impact. But the problem is that they're restricted to clinics and hospitals. In a daily healthcare situation, you have lots of these health data that are being generated that the CDSS does not have access to. So there is this information gap. And when you go to a clinic or a hospital, you're asked, well, what are your symptoms? And we are not very reliable in terms of recounting our symptoms or recognizing which symptoms are more important than which others for our health condition. So let's look at if you try to combine these sensors, wearable medical sensors, with CDSS, what kind of a system you could come up with, and could we try to address some of these problems with this kind of a combined system? Okay, so currently there are no solutions for wearable medical sensor-based disease diagnosis. I'll just present one in a few slides, but that's very early work. The state of the art is that you have these sensors, and if you are above a threshold, you raise an alert. So it's just a threshold system. And the problem is that these thresholds should really be individual specific, because even for one individual at different time and location, the threshold ought to be different. So that's a problem that makes it too weak for doing disease diagnosis with these threshold systems. And when we say smart, there is an implicit assumption that there is some machine learning going on. In healthcare right now, the data sets that we have need to have a label. So what we are doing is supervised machine learning. However, a lot of the data that are collected in healthcare do not have labels. It's very expensive to have an expert label the data. So there is a need, and that's an unmet need, of doing unsupervised machine learning or semi-supervised machine learning, where you have labels for some of the data, not all of the data. But in this talk, because currently the state of the art is supervised learning, I'm going to limit myself to that, but there are a lot of problems in semi-supervised and unsupervised learning that one has to address in the coming years. I just wanted to point that out. Now you can do various things. So if you remember, the curse of dimensionality problem says that if I increase the number of features that I extract from the data set size has to exponentially increase to maintain the accuracy. Now in healthcare, that's a big problem. Our data set sizes are very small. It's not like the images and like the ImageNet, which has a million or more images. Our data sets are very small in healthcare. So we don't have the ability to grow the data set exponentially as we add more features. So it's extremely important to reduce the number of features without giving up on the classification accuracy. So feature filtering becomes very important. Throwing away the redundant features, keeping only the informative ones becomes very important. And we can have many different types of base learners. There are lots of machine learning algorithms. In this domain, generally, neural networks don't perform very well because we don't have the training data set sizes that we need. So we can come up with various base learners, have another meta learner on top of that. Simplest could be just majority or average, but you can do something more sophisticated to boost up the accuracy of whatever you're interested in, for example, disease diagnosis. And there are lots of these workbenches that have now become available that ease the process of doing these experiments. So let's look at HDSS, which is really a combination of these wearable medical sensors and the CDSS. It's a multi-tier structure, as we'll see. And its contributions are that it shows that it is feasible to do reasonably accurate disease diagnosis. And it can scale potentially to hundreds or thousands of diseases. And my grad student tells me that there are something like 69,280 diseases. And if you open up a medicine book, you'll find 20 different chapters. Those are the 20 different disease categories over which these 69,000 diseases are spread. And if magically we had data sets available for all of these diseases, then we estimate that you will only need about 62 gigabytes of storage to store all the machine learning models. So this is well within the realm of technology that exists today. So you could, in parallel, monitor all the diseases and see if there's a disease onset for any one of them. So that's maybe a decade away, but the key there is not the machine learning algorithms. The key there is a lack of the data set. That is what is preventing us from achieving this goal. So let's look at HDSS. Here you have tier 1, which is based on wearable medical sensors. And you do some diagnosis, and if there's a disease onset, you tell the patient, the individual, to go to the other side, which is beyond the clinical boundary, the clinic or the hospital, where you have these tiers. Tier 2, the physician is going to ask you for your symptoms, do some simple tests. Perhaps those simple tests are not good enough, so then you go to tier 3, where more sophisticated tests are ordered, like MRI, CT scan, blood test, etc. And then finally, you have tier 4, where you have these post-diagnostic decisions, treatment, prescription, lifestyle, etc. And all of these tiers, all the 4 tiers, interact with a diagnosis engine. So there is a model at each level, each tier. So there's an interaction both ways. You supply the data to the engine, and the model comes back from the engine. So that's the high-level view. So let's see what the lower-level view could be. So let's look at tier 1. So we have all these wearable medical sensors at the top, and there are these context recognizers. So sometimes, if I'm running, some of my physiological signals are going to be so noisy that they should really be thrown away for that duration. So we have lots of other sensors. In our smartphone, we have accelerometers. Even in some of these smartwatches, we have accelerometers, which can very easily determine what my physical activity currently is. So that recognizes the context and tells me whether the wearable medical sensor data at the current moment is something that is useful or not. And then you do the typical things, cleaning missing values and feature extraction, converting continuous features into categorical features, binning them, and come up with bunch of base learners and a meta learner to boost the accuracy, and ultimately have a model that gives you a signature for that disease. If there is a disease onset, perhaps the physician would be interested in knowing what was your physiological signal before that rare event occurred and just after. So you also record the data to send to the health server and send the individual to the clinic after this. And you can, in principle, monitor all of these diseases for which you have these models in parallel. So we have already lots of these sensors on our body. The B-class sensors are the ones that are collecting the physiological signals. M-class are the motion, and L-class are the location sensors. And they come in various form factors. And the M and L-class sensors are really recognizing our context. What is our physical activity right now? In fact, you can also recognize the emotional activity. Our emotional state is betrayed by skin conductance. So if you're monitoring the skin conductance, the sensors can also figure out, understand what our mental condition is. But in this talk, we are just using the M and L sensors for recognizing the context, and then helping provide that context to the B-level sensors to see if those have become too noisy because I'm running or doing some other heavy activity. So let's go on to tier 2. So now there's a disease onset. I've gone to the clinic or the hospital, and let's see what a human would do and what HDSS would do. So a human, the physician will ask you some questions, make some observations, look at the electronic health record, order some tests, and they have lots of table lookups in their brain. So the input is all the symptoms, all the data that have been collected so far, and the output is some kind of a diagnosis. And then you either go to tier 3 or tier 4. With HDSS now, you could automate a lot of that. You have the same sensors, you've got the disease onset. Perhaps here, the number of tests ordered would be even larger than on the left-hand side, because the HDSS is not going to forget any test. Physician may forget some of the tests. And then you clean up the data, get the model, and again go to tier 3 or tier 4. So it's very similar, parallel things that a human could do. Now we can also automate in HDSS. Then you go to tier 3, because maybe for some diseases it's not enough to look at the sensor data or the tier 2 data. Maybe you need an MRI, and so more sophisticated tests are ordered. These are more time-consuming, more expensive, so we try to avoid these tests if possible, but when needed, you need these tier 3 tests. And then you go on to tier 4, where you have these post-diagnostic decisions, and then if everything is okay, you go back to tier 1, and now you're in the daily healthcare monitoring mode. Okay. So how would you verify the efficacy of a system like this? So we searched for data sets, and they're very scarce. So there is a source, UC Irvine, and they had 360 data sets, but only 5 of them, which are listed there, had the labels for specified diseases. And those are the 5 diseases. And the number of instances tells you how many rows, how many individuals were monitored. And number of features is the number of columns in your data matrix. That tells you what features were extracted. And the number of classes tells you the different levels of the label. So for example, there are 16 types of arrhythmia that you have to distinguish among. But for diabetes, it's either diabetes or no diabetes. So it's only a two-way, a binary classification. So let's look at arrhythmia and see how we could go about coming up with this model. So these workbenches are available that you can exploit. In this case, the assumption was that the wearable medical sensor is a 12-lead vest that you can wear. And there are lots of these base learners that are listed on this side that we can use because of the no free lunch theorem. In machine learning, you know that there is no guarantee that a particular machine learning algorithm will dominate some other machine learning algorithm for all data sets. So you have to try out all the algorithms to see which one does better. And then you can do a meta-learner on top of that. You collect the outputs from these base learners and then somehow come up with higher level intelligence from the meta-learners. And you, of course, to counter the curse of dimensionality, you also have to do filtering of the features. And then you do standard cross-validation. And for arrhythmia, it took 1 CPU day to come up with the model. So if you compare it with the threshold method, so if you look at the graphs here, this is all for arrhythmia, and this is arrhythmia first for the binary case. Can you just distinguish between arrhythmia and non-arrhythmia? So if you look at these base learners, the first bar for each of the base learners is for the case where only the base learner is used. The second bar assumes that now you've done filtering to reduce the number of features. The third bar in each group refers to the case where you also have a meta-learner, some ensemble method, and the fourth bar combines all of them. And then you, if you look at all these different combinations, the random forest wins with about 86%, if I can, yeah, 86%. And this horizontal bar that you have, that tells you what accuracy you'll get if you just use a threshold method, which is about 67%. So you can get much higher accuracy with these wearable medical sensors. So it's feasible to do disease diagnosis this way. And let's look at it in somewhat more detail. So these 5 data sets that were available, one of them, acute inflammation, actually has labels for bladder disorder and the pelvis disorder. So there are actually 6 diseases covered by these 5 data sets. And here is a slide that gives you a sense of the diagnostic accuracy. So DM1 here refers to the diagnosis module for tier 1, DM2 for tier 2, DM3 for tier 3. So obviously, more and more sophisticated tests are ordered when you go from tier 1 to 2 to 3. So you would expect the accuracy to go up, going in this direction. The only exception you see here is with wearable medical sensors, you get 86% for binary classification. Here it's 16-way classification, which is a much tougher problem. So the accuracy goes down because you're tackling a tougher problem. But in all the other rows, going from left to right, the percentage would increase. But what is surprising is that just by doing binary classification for all these diseases, in tier 1, breast cancer, there was no wearable medical sensor data available, so there's nothing here for tier 1. But for all the others, you can see a reasonable accuracy, 78% to 99%, is feasible just using wearable medical sensors. In the parenthesis, you have the previous state of the art, so the accuracies are comparable to what has been obtained before. But the key column is this one, where it shows the feasibility of getting reasonable diagnostic accuracies for these test sets. The problem is that the 20 disease categories that I mentioned, we looked at 4 for which data sets were available. We found another 5 disease categories for which data sets are available, but they're private. They're not on the web. So if they had been available, we could have applied HDSS to it. But for 11 of the disease categories, there are no data sets available. So that's a wide open area of research. In fact, we are teaming up with a local mental health clinic to look at, to collect data sets for bipolar disorder, anxiety, depression, and so on, to see if this approach is extensible to something like digital psychiatry. But it's a wide open area to tackle all those 11 disease categories for which we don't have any data sets. So let's look at smart healthcare from another direction, which is related to HDSS, which is stress detection and mitigation. So stress is the second most common health problem in Europe. 75% of the doctor visits, even in the US, are stress related, and the expense per year is 300 billion. And this is by no means an exhaustive list of stress-induced health problems. So obviously, if we can detect stress as quickly as possible, and try to mitigate it as quickly as possible, it helps us in the long run because all these stress-related disorders hopefully get postponed or never happen. So this system called SODA for stress detection and alleviation, it collects the data from these wearable medical sensors, does local inference, classification, and if it finds in real time that you're stressed right now, through an app, it communicates with you and recommends some stress mitigation techniques. So when this experiment was done, all these wearable medical sensors were discrete, and these were the different parts of the body where they were located. This is a year and a half ago, but since then, these sensors, a lot of them have been consolidated, so it's much easier to wear these sensors now. And it's supervised learning, so I have to collect labels. So that means I have to know when you're stressed and when you're not stressed. So we collect some data from your wearable medical sensors when you're not stressed, and then we artificially stress you. Some ways of doing that would be to give you a memory game and not give you enough time to finish it. Or have a fly sound near your ear, it's really annoying. Show you some pictures that induce stress, or ask you to put your hand in an ice bucket. All these things are very stressful, and when we have exposed you to this stress, we collect the data and we label that data as being stressed and the previous data as not being stressed. So that's our labeling, automatic labeling method. So out of the 5 sensors, there were 90 features that were extracted. This was for 32 participants across campus. And these were reduced to 15 features without much loss of accuracy. And you can do this modeling in 2 ways. One is for the individual. It takes about 2 hours of data collection per individual. And we can have a model for that individual, but then it means that you have to sit down with us for 2 hours. Or we can pool this data together from 32 or whatever number of individuals you collected the data from, and come up with a population level model, and that you just download as an app and start using. So you would, as you would guess that the individual level model would have a higher accuracy, and that's what you see. It's 96% stress detection accuracy if you allow us to collect data from you for about 2 hours. And otherwise, if you're just applying population level model to you, then it's only 89% accuracy. But these, again, are much more accurate than what you'd get from just a threshold sensor, which tells you above a certain threshold, they raise a stress alert, and below that, there's no stress. So when a stress has been detected, your app will prompt you to do some stress alleviation techniques. And what we found was micro-meditation really helps within a minute. And all you do is close your eyes and just relax all your muscles from the toes to the head, just for a minute. And we can see on the wearable medical sensor data, it has an impact within 1 minute. Then a lot of you may be getting your news from news.google.com, where most of the news are bad, makes you depressed. So there is actually a site called goodnewsnetwork.org. You can try it, where all the news are good. And that also de-stresses you within a minute. Holding a warm stone in your hand is de-stressing as well. And we had thought that classical music should also be universally de-stressing, but we found that out of the 32 participants, maybe around half of them, it worked, and the other half were immune to the charms of classical music. But it's also a tool, and I'm sure you can investigate many other techniques, take a deep breath, all those things you can test with your wearable medical sensor in this machine learning model if it is having an impact, a quick impact. So as soon as the stress is detected, if it is alleviated, then hopefully our stress-related disorders will become less common. Okay. So now let's look at this pushing of intelligence all the way down to the edge nodes and even to the extreme of the edge node, which is the sensor node. In the past, these sensor networks were wired, but they have become now wireless. And we have these wireless communication protocols, Bluetooth Low Energy, Zigbee, and so on, that allow you to transmit the health data quite a distance. And there are other techniques which are much lower energy, like impedance modulation, but they only let you transmit the data 1 to 5 centimeters. So what you can do is have gateways that allow you to, so you first transmit the sensor data to a gateway, and that gateway communicates with the base station, which is farther away. So that's the current way these sensor data are propagated further. And there's some local signal processing that is done on the gateway, and the aim is to reduce the end-to-end system energy. And it's not just for smart healthcare. In other IoT applications as well, environmental monitoring, you could apply the same paradigm. And what happens is that if you look at the medical data that we are collecting, there are two problems. One is the bandwidth limitation, even though the bandwidth required is actually quite small. So if you look at this protocol, MICS, the Medical Implant Communication Service Protocol, you can overwhelm the bandwidth that it can support very quickly with the increase in the number of recording channels. So bandwidth becomes a problem. I cannot transmit too much data too fast. And energy becomes a problem. So it's not the analog to digital conversion energy that gets us. It's really the transmission energy. So if I have an ECG sensor that is transmitting 10,000 times to my smartphone per second, that transmission energy could be about 99.9% of the sensor energy. So if we could somehow do more intelligence locally and transmit less, we can save a whole lot of energy while making the sensor smart. Okay, so making the sensor smart actually can improve the energy efficiency also, which seems counterintuitive because you're doing more on the sensor, but you are saving a lot of transmission energy, and you're only increasing the computation energy slightly. So we have to represent data more efficiently. One way to do that is called compressive sensing. So Candice and Donahoe about 20 years ago invented this idea, which goes away from Nyquist sampling. So Nyquist-Shannon theorem says you sample at twice the frequency, and it's a necessary and sufficient condition, it's optimal. What Candice and Donahoe said, well, what if I can tolerate 1 minus epsilon probability of reconstruction? If you can tolerate, and because a lot of the sensor data is noisy anyway, so it's okay to tolerate 99.9% accuracy as opposed to insisting on 100% accuracy. So it exploits that fact, and it says that if you satisfy one condition, which is very easy to satisfy, that this signal is sparse in some other domain. The EEG signal is sparse in Gabor basis, but that condition is easy to satisfy for most IoT signals. What you need to do is just take this data, run it through a random projection matrix, which is a very simple matrix. The entries are +1 or -1. You toss a coin. If it's head, it's +1. If it's tail, it's -1. So it's very easy to generate this matrix. And all you do is just matrix multiplication to get the compressed signal. And then you reconstruct, and you can see that the reconstructed signal is very close to the original signal. So you can compressively sense, transmit the data to the base station where the signal is reconstructed. You're back in the Nyquist domain. You can apply all your favorite digital signal processing algorithms. The problem is that the reconstruction is accurate, but it's very energy intensive, as we'll see in the next slide. So this is a great idea, but the state of the art would be compressively sense and transmit. You save a lot of energy because you've now reduced the communication energy, but not enough because you didn't do any signal processing in the sensor itself. You have to come back to the original reconstructed signal, and that is very, very energy intensive. So for example, here we see for 2 application spikes and EEG, and this is a log scale. So basically, if you look at the sensing or the compression energy is very little, but reconstruction energy is 3 to 4 orders of magnitude higher. So I cannot possibly reconstruct the signal on the sensor node itself. So that was a severe bottleneck in the past. So you would not reconstruct on the sensor, you would reconstruct somewhere else. And another bottleneck that we faced earlier was that when you've compressed the signal, it looks something like this, and your traditional Nyquist domain signal processing algorithms no longer work. So how do you process these signals? That was also a concern. So there is now a solution and where you don't have to reconstruct, and you can do inference, both feature extraction and classification in the compressed domain itself. Proof requires a lot of linear algebra. I didn't want to bore you with all the proof here, but net result is that for different smart healthcare applications like neural prosthesis, epileptic seizure detection, you can reduce the amount of computation significantly, 54x and 21x in these two cases. And the net impact on the sensor energy is about an order of magnitude reduction. So now you've pushed inference all the way to the sensor level. So here is another angle. So I want to monitor my health 24/7, year after year, decade after decade. So is it possible to do it storage efficiently and energy efficiently? So here are some of the wearable medical sensors. This tells you what the bits per sample is, the sampling rate, multiply the two, you get the transmission rate. Based on a coin battery that these sensors have, this tells you what the battery lifetime is. And if you look at the ones in red, ECG, EEG, they consume so much energy that every 0.4 days, which is less than 10 hours, you have to recharge the battery. So I don't know about you, but if you ask me to recharge a battery every 10 hours, I'm just not going to use it. It's just too cumbersome to use to remember to recharge the battery that often. So this battery lifetime has to be increased for these sensors to make sense and become practical. So what you could do is we could think of a couple of things. So most of the IoT sensors are just sense and transmit. Analog signal is sensed, converted to digital, and then you just transmit. You could aggregate the samples and then transmit. So you have to energize the transmitter less often, and you can save some energy even though you're still sending the same amount of data. Or you could do Nyquist domain inference where you're looking for those rare events. So what's the point of my ECG sensor telling my smartphone 10,000 times a second that I'm not having an arrhythmia attack right now? So most of the time I'm not having an arrhythmia attack or a heart attack. When that rare event does occur, that is the time when we should tell the smartphone to get an ambulance and collect some of the data before and after and send that to the health server also, because the physician may want to have a look at it. You could do that in the Nyquist domain, or you could also now, because we can do it in the compressed domain, you could do the same thing with compressive sensing. So here is just one application. You can apply that to many different applications. But the traditional ECG-based sensor, and this is for arrhythmia detection, the battery lifetime, as we saw earlier, was only 0.4 days. And for 1 year of data, it's about 44 gigabytes for this just one sensor, for this one application. If you aggregate, it's still 44 gigabytes per year, but now you've increased the battery lifetime a little bit. Now, if you're doing inference in the Nyquist domain, lifetime has gone up to 26 days. The amount of storage has come down dramatically because the rare events are rare. And in the compressive domain, now I have 136 days of battery lifetime and only 2 megabytes per year per person. So that makes it very practical. You can do this for many other applications as well. Now let's go on to security, because this is often overlooked in our enthusiasm to introduce new sensors, new devices into the market. The last thing we think about is security, but in the future perhaps we should think of security at design time itself. So there are lots of these implantable and wearable medical devices that have become common, and they are IoT. Basically, they have sensors, they have actuators, they have processing elements. There is a programmer that the physician uses to communicate with these devices. You have cardiac, cochlear, neurostimulation, all kinds of implantable devices and wearable devices for insulin pump, for glucose, and so on. Now, so let's look at these wireless attacks on medical devices. So in 2008, a group of researchers showed that if you have a pacemaker it can be hacked from a distance. So it can be sent a command that causes a heart attack, and that's from a distance. In March 2008, some hackers showed that if you visit a particular website, by showing you some images, they can trigger an epileptic attack. In 2011, we showed that an insulin pump similarly could be hacked from 20 meters away. And then there were some other demonstrations of attacks on insulin pump after that in 2011 and early 2012. So if you look at insulin pumps, there are about 30 million diabetics in this country, 9% of the population, and there are 5 million insulin pumps that are being used in this country. And the different components, they talk to each other wirelessly. So there's a glucose sensor, there's a glucose meter, there's an insulin pump. They all talk to each other wirelessly. So you can eavesdrop on those wireless signals. None of them are encrypted. And perhaps you can reverse engineer the communication that is going on, which is exactly that was done in this attack which hijacks an insulin pump. And the equipment you require is only a software-defined radio. The software is free. The frequency at which you have to monitor this is known from FCC. There's no secret there. You can eavesdrop on those wireless communications and then do some processing to figure out what is going on. So you collect publicly available information, frequency modulation for the insulin pump that we looked at. It was on-off keying. You reverse engineer the packet. Here is the packet for the insulin pump. We didn't give so much detail in the paper that you could actually replicate our attack, but we gave enough detail to convince you that we had done the attack. But this is the packet, and here the information. You can insert your malicious payload, make the CRC check, everything else pin, everything work out. So when you send this packet to the insulin pump, it has no way of knowing it's a malicious packet. And you can order the insulin pump to pump in too much insulin or not enough insulin into the body. Okay, so what if the attackers could eavesdrop? So that's just a privacy problem, that you find out that I have diabetes or hypertension. You could capture a previous packet and replay it later on. That will change the amount of insulin being pumped, so that's dangerous. But C is a real dangerous one, which is an integrity attack, that I can now control the insulin pump and make it do whatever I want it to do from quite a distance, from 20 meters away. You could, if it is a pacemaker, you can send a packet to it that keeps failing the CRC check, but keeps draining the battery. And changing the battery for the pacemaker typically is done every 10 years or so. So if you drain the battery of the pacemaker, now the surgery has to be done much earlier, and there's a 2% failure rate in surgery. So this draining of the battery attack is also, even though it fails, but by repeatedly doing it, you can cause malicious things to happen. All of the above are possible. From how much distance? The eavesdropping could be done from 7-8 meters. Of course, you have a more powerful transmitter receiver, then you can bump up this number. And controlling the integrity attack was possible from 20 meters away. So we have to look for solutions, and there's a lot of legacy hardware already out there, a lot of pacemakers, a lot of insulin pumps, 5 million users in the US of insulin pumps, lots of users of pacemakers. So here is one technique called MedMon, where you look at different anomalies, physical anomalies, for example, received signal strength, the time of arrival, differential time of arrival, angle of arrival, and you look at different behavioral anomalies like the range of insulin, is it in the correct range, rate of change, is it in the correct range, frequency, and only if you pass all of these tests are you allowed access to the medical device. Otherwise, just in time, your malicious signal is jammed. So this is just one approach, but there are lots of other approaches that are required. In 2011, actually, FDA issued an advisory to all the manufacturers of these devices to take security into account. So my guess is in the future devices, you will have encryption, but in the current devices, you don't have encryption, and all of these attacks are possible. So that's what I have to say. And here we looked at smart healthcare from various directions, and I hope I convinced you that there are lots of open areas, especially in disease diagnosis and security, energy efficiency, that deserves much further investigation. So hopefully it may spur some of you to explore some of these problems and come up with innovative solutions in the future. Thanks a lot.
Hello, sir. Do you think it is not possible to actually forego tier 3 when you're using HDSS? I mean, in tier 2 itself, you could actually include the tests and...
Yes, for some of the diseases you found, let's say 99.6% accuracy, then tier 1 is enough. But I would suspect for cancer, tier 1 and 2 would not be enough. So you would need tier 3 for some of the diseases, not all of the diseases.
I have another question up here.
Hi, sir. I have a interesting question. Do you think about some psychology issue about the system? If some sensor on my body and 24 hours a day to monitor my blood pressure and continue send me signals whenever the pressure get high, in long term, kind of people can generate some nervous or worried too much about the healthy. Do you think about the psychology issue about such a long-term monitoring system?
Yeah, so if I get your question, it's basically that these wearable medical sensor data are collecting so many physiological signals and they're wirelessly transmitting it to the smartphone. I eavesdrop on it, and now I can figure out a lot of your health conditions. So even your psychological state right now, I can figure out. So definitely, if you don't encrypt, that privacy loss or that privacy risk is still there. If you do encrypt, what happens is you need 2.5 times more energy. So you drain the ECG sensor or EEG sensor even faster. And it was already down at 0.4 days, and reducing that further is going to make it even less practical. So you do need to combine that with other things. For example, inference on the wearable medical sensor will allow you not just to have inference. Now you save so much energy in the transmission that you can also put AES or SHA-3, you can do hashing and encryption also without paying a penalty in terms of energy. So that's something that we have also done. And surprisingly, we are getting about 200x lower energy compared to the sense and transmit case. So you're doing more, you're putting smartness and security on the sensor, yet you reduce energy by 200x because you save so much on the transmission energy. So there are ways to tackle that, but the current sensors do not give you that protection.
So it was interesting that I think at one point you said it took about 62 gigabytes of storage to store machine learning models for 69,000 diseases for this HDSS system. With the declining price of storage, that would make that model widely accessible in not too long a period of time, wouldn't it?
Yes. So that's, according to our estimate, even today, I can afford 62 gigabytes on my body.
Yeah.
And we probably cannot tackle all the 69,000 diseases, just like the first question. Perhaps cancer cannot be treated or diagnosed with wearable medical sensors. So it may not be 69,000 diseases. It could be just in a couple of thousands. But yes, the key problem is lack of a data set. And we have started this process. The IRB approval process at Princeton takes forever. But hopefully next week we'll have the approval to start collecting the data sets. But we need lots of these data sets for all the 20 disease categories.
All right, so you mentioned the consolidation of sensor networks into individual devices. I'm right here, right behind the cameras.
Okay. All right, yeah.
So you talked about the consolidation of sensor networks into single devices or fewer devices. What are your thoughts on the opposite end of the spectrum, where we have much lower cost, smaller devices that you might swallow, basically massive sensor networks within the body, temporary? Any thoughts or visions on that area? Yeah, smart pills, essentially.
Yeah, great idea. In fact, we have a professor in our department who's doing exactly that. It's ingestible sensors that will report on your health condition from inside. And more sensors, the better, because now you extract more features. In fact, I would go further. If you look at IBM Watson, there was a 60-minute segment on IBM Watson, and it said that it reads 8,000 oncology papers in a day. And it extracts features from those 8,000 papers, and no oncologist can match that reading ability. So there'll be data coming top-down from electronic health records, from reading papers. So it's a top-down method that IBM Watson is following. What we are advocating is a bottom-up method, starting with the wearable and ingestible medical sensors. These two, in the next few years, have to meet in the middle, and our genome data will become available for $100. So I can extract a lot of risk factors from the genome data also. So the number of features that we can extract will become more and more sophisticated as time goes by. And so this diagnostic accuracy will go up dramatically, maybe by 2030. So it's just a question of collecting all of that data.
So I think we have time for one more question. Here it is.
Sir, you said that there's no data for the 20 categories, but is it not possible to actually, like, using GANs or some kind of technique to actually, like, generate data, I mean, virtual data that could actually help in probably moving the research forward?
Sure. So GAN would be a great idea if you knew what the probability distribution was from which to generate the synthetic data. So we need some A data set, and then if that data set is not big enough, it has only 200 instances, we can use GAN to populate with synthetic data, which are drawn from the same probability distribution, and make it 1,000 data instances. But that still presupposes that you have some supervised data, some labeled data available, and that is what is missing.
Panasonic.